I did like 1 hour homework. Yeah, I mean, I was pretty prepared for my college experience, but it wasn't because I had a.
No, you were prepared.
Prepared in terms of I worked hard in high school, so I was ready for college. But I was prepared in the sense that.
Yeah, I don't know. I think the hard time I worked in high school is we had 1 semester where the entire semester, the entire quarter, I don't know, right in the it wasn't even that hard, it was just annoying.
But it was all just like spending 25 hours. It's really I don't really know what he does. Apparently he does not all So what's the adjustment? We think it's zero. There's no current in the coil part. And you're going to have to just put the individual wire. Yeah, you can change the rotation.
Okay, can you hear me? Are there any questions before I get started? No questions. Let me make a roll call then.
Muna awalan, saling bersama, Arabin Shankar, Olimpo, Yuhan Chen, Saling Profit, Wang Qin, Adam, Zedong Tu, W. Thomas Manel, Dr. Lakshmi, Yu Ping Lee, Jeffrey Market Sanchez, Ira Marinova, Logan Malachi, Sophie Thompson Hayes, Ryan Snyder, Wukun Tan, Brendan Triplett, Ao Van Wong, Ye Wong, Yua Hua Wu, De Yang, Joseph Zulu. Okay.
Let's continue with the lecture on transmission lines. I suppose it's a topic that you have studied before as an undergraduate, so this will be very much like a revision for you. How many of you have not had transmission line theory when you were an undergraduate?
Okay. You can read the frequency notation. This is thing that I write up. I think
The lecture notes have been written up quite comprehensively, and you should be able to understand the lecture notes without a prior knowledge of transmission lines. And if you have a problem, let me know, or let the teaching team know. We can talk to you individually if you need more tutoring. But how was the last lecture by Bo Yuan Zhang on transmission lines? It was good, wonderful.
so. In the last lecture, you know about transmission line theory, and then you know when you have a transmission line, you have two kinds of ways. One is propagating to the right, the other one propagating to the left, and that's set up a carrying weight on the transmission line. And we also set up a kind of sequence that is a function of degree. Those voltages and currents are not functions across the transmission line. And you know how to connect transmission lines together using the junction. But what I like to call here is that junction is not simple junction as you see in the picture. You can just draw junction of the transmission line. But
Okay, the two transmission line, you can say one, two transmission line one, this has 0, 1, and then connect it to a transmission line with a different impedance. This is not realistic. When you connect two transmission lines together,
you have two waveguides or corrected cables or something that you can think of that are quite different in the length in geometry, and hence there will be some discontinuity at the junction between the two transmission lines. So the discontinuity gives rise to two effects. One is that the might be sharp accumulation at this junction, and those
give rise to excessive capacitance. For instance, if I make a transmission line out of microstrip line, okay, you can have this You can have this transmission line very easily made. What you do there is that you have the substrate, the ground plane, and then on top of the substrate, this is epsilon r not equal to 1, and then you just etch another line. So very easily you can make a waveguide, a microsweep waveguide, which behaves like a transmission line.
And say you were to connect two of these transmission lines together, you get like to such accumulation of junction because the current cannot flow smoothly.
Just imagine that if you have a current flowing here, okay, they don't flow smoothly from line 1 to line 2, giving rise to such accumulation of junction. Those values can be modeled as either F in this picture. And also the current flow might be some friction. okay, there might be a rush of current flow because of this junction discontinuity. Maybe the junction in the first line, the current in the first line is more intense than normal, and you have more intense current that is like the more magnetic field, and those magnetic fields in the model as inductive, the straight inductive. So usually you have to add some lump elements at the junction between two waveguides, the transmission line. And of course, you know how to solve this problem quite easily, since you already know how to solve the transmission line part using Smith chart. The other part is just circuit theory. Okay. Any questions on this? So I presume you know how to calculate the voltage here, and then calculate the impedance here, and then calculate the impedance again using series parallel connection of lump elements. Okay. So if you don't have questions, I'd like to talk about duality principle. Duality principle exploits the symmetry of Maxwell's equation. And if you were to write down Maxwell's equation, they are beautiful in the sense that some kind of symmetry exists, like if you write down Faraday's law, it looks something like this. And of course, we have said before that we can add a magnetic current, which is not there in the real world. It is a kind of fictitious quantity, but that doesn't prevent us from adding this current to Maxwell's equation. And then you can write down Ampere's law in its full glory. Then you will have a displacement current form. Well, an electric current form. And now if you look at these two equations, they are very similar to each other, except for the symbol.
Okay. One has B, the other one has C, and the rest of E and H and H.
So they result some kind of a symmetry. And if you write down the other equations, which are derived from the first two, your divergence of B, R omega is rho of E, R of omega, you can get divergence of B. R omega is equal to rho of M R omega. Those are the third and the fourth Maxwell equations.
How would you derive the third and the fourth Maxwell equation if you know the first two? There is a triple divergence for the first equation left hand side to the 0, then the divergence of B, and then the triple divergence of M becomes one related to the fast density, magnetic fast density, and you get the last equation. If you see the divergence of the second equation, you'll get a second last equation. But again, you know that equation is highly symmetrical. Last equation is the third last equation, looks almost like each other except for the symbol.
Because of this, what it says is that if I have solved these four equations and obtained a set of solutions, it says that if I were to do some swapping, where I replace my E with H. And I replace my H with minus E. And then replace B with B. And then B with minus D. And the N with minus J. J with N. Rho N with minus rho E. Rho E. Rho E with rho N. Okay? It's a simple mathematical swap. If you solve this four equations and solve all the unknowns, and if you do the following copying, you replace E with H with minus E, and the four equations B with B and B with minus B. You find that the equations remain unchanged, and you will further require that N becomes minus K, J becomes N, rho of N becomes minus rho of E, and rho of E becomes rho of N. These four equations are rectified, so it's just to see the four equations. It means that once you have solved these four equations, you can create new solutions by different these problems. Does this make sense? Okay. So you can find new solutions very easily without having to do extra work. You just plot the field and you get a new set of solutions. And if you have material media, like D is epsilon dot E, B is mu dot H, an isotropic material, then you have to do this further swap. That the permeability tensor got swapped to this, and then the permittivity tensor got swapped with permeability tensor. And then Maxwell's equations will remain the same. Okay, this is all exploiting the symmetry of Maxwell's equations. And we will use this to find shortcuts to solutions. And if we found solutions, then we can get new solutions quite easily. For instance, if you have a plane wave on the left, okay, and then if I do the swap, as I said before, E with H, H with minus E, okay, I get this other solutions over here. And it's important to see that E cross H points in the K direction or the beta direction. Many textbooks will use K, but we also use beta, which is the wave vector. And we do this very simple swap, as we have said before. You get from the left picture to the right picture. When you see that, and the right picture is still a solution to Maxwell's equation. This is the simplest case. A plane wave propagating in free space. Okay. Furthermore, this swap preserves the right-hand rule. E cross H points in the K direction. Okay. However, you can do some unusual swap where you change mu with minus mu naught, epsilon with minus epsilon naught. You see that the wave is not right-handed anymore. E cross H will not be pointing in the K direction. Those are called the left-handed materials. Okay, and those are called double negative materials as well, where you can assume that both mu and epsilon are negative. Then you can easily show that right-hand rule does not apply. You have to use left-hand rule for such a kind of material. Okay, I discussed this more in the lecture notes. And this kind of like double negative materials, left-handed materials, has recently become a very hot topic. It actually was proposed by Vitalago many years ago in the 30s, I believe. But nobody paid attention to his proposition. But recently, John Pendry, okay, proposed this again, and he claims that you can get super resolution out of this kind of thing, or you can get time reversal symmetry. Coupling this thing in replacing mu with minus mu, epsilon with minus epsilon, it's the same as changing omega to minus omega. So if you look at this equation very briefly, if I change omega with minus omega, that is amounting to replace mu with minus epsilon with minus mu. So if you do a omega to minus omega swap, that is the same as changing time, okay, because all the time harmonic signals that we have this kind of time dependence. And if you were to change omega to minus omega, you get this. But if you change t to minus t as well, the solution is resolved. So from plus omega to minus omega is the same as changing time or doing the time reversal. I will not discuss it very much. This is not necessary for this course. It's just something interesting to note. But are there really magnetic currents in this world? That is the question we like to ask ourselves. It turns out that you cannot make magnetic monopole. Nobody has found a magnetic monopole yet so far. However, we can make magnetic dipoles. And a magnet, a permanent magnet, is a magnetic dipole. And it comes about because of the spin of the electron. Electrons have spin, protons have spins, and those are actually like very little magnets. There is material, and this little magnets can form domains, and then when you build up the domains, you can see magnetic dipoles in many real materials. But you can also make a magnetic dipole quite easily. Here, this example of the electric current loop. The first picture shows the field of an electric dipole. And you have done the homework before, you can convince yourself that the electric field is as shown here, it's pointing in that direction. And the electric dipole is just the superposition of two monopoles of opposite polarity. You can imagine in your head that the electric field is like that. So now if you take a current loop and you pass the current through the current loop, then you can invoke your ampere. Put your finger around the current loop and you can figure out which direction the magnetic field should be pointing. And if the current is going in the loop, you can show that the magnetic field must loop around the current loop in this manner as shown in the bottom picture. And if you're not in the center of the current loop, you're far away from it, you will see that the second magnetic field looks like that of a dipole. Looks like the electric field of the first picture. So the electric current loop actually produces a magnetic field that looks like that coming from a magnetic dipole. Are you convinced of this? I guess as you know, from knowledge. So it's quite easy to make magnetic dipoles in the electrical engineering. You can actually line up this magnetic dipole and make a pole. This is called a toroidal antenna. So if you line this thing up, you can get magnetic field to go around in the loop. And if magnetic field goes around in the loop, I can think of this as being acting like a transformer. Okay. The currents in the first loop or the toroid can be thought of as the primary turn of a transformer. And you can imagine another loop, say if you were to connect this outer wire to infinity, you can think of the other loop as a secondary turn of a transformer. And then by passing currents into the toroid, you can force currents to go in the other loop. What happens is that this toroid actually acts like a magnetic current source. So roughly speaking, you can think of this toroid being alignment of magnetic dipoles that is actually the same as having a metal with the magnetic current going around in a loop. Okay, magnetic currents are usually indicated by double arrows. So you can go through your, not actually Ampere's law, the analogous of Ampere's law is current. So electric current produce magnetic field in the loop. Magnetic current in the loop will produce what? Electric field. Very good. So you can imagine yourself that this current loop, magnetic current will produce an electric field if they are in free space. Okay, they will produce electric field, something like this. Okay, electric current will produces magnetic field, but magnetic current will produces electric field. So what happens is when you wrap a magnetic current loop around a metal like this, you will produce electric field that goes like this. Okay, and then it goes inside the conductor, and hence it will produce a voltage drop from the top part of the metal to the bottom part of the metal. The magnetic current loop can be used as a voltage source in electromagnetic. In fact, this kind of thing has been used in the oil industry in something called the mode 2. Okay, and then this toroidal antenna will launch a wave that looks like this, and it almost looks like a coaxial cable, because if you take a top view of this thing, the electric field will go like this, like what you see in the coaxial cable. And this mode is called the Goobel mode. Okay, it's called the Goobel mode, and it's been used in the oil industry. Any questions on this? So let's see how we can use duality principle to help us solve problems. Say if we know how to solve this problem, reflection by a single interface gives graphic division, great mathematical detail in the middle moment. So I think work very hard. Spend the whole afternoon solving this problem. It's very complicated. Okay. Is the solution worth it? Well, it's worth it if you know how to use duality principle, which says that if I solve the first problem, I can easily find a solution to the second problem by duality. I have great savings in labor. Okay, I don't have to do the work twice. And this is, of course, the single interface reflection problem that you might have studied before in the undergraduate course. How many of you have not had single interface reflection coefficient study before? I guess some of you have, right? Single interface reflection coefficient. Brandon, you have your optics class, so you should know. Okay. So the next thing I like to study is the reflection and transmission of waves, same wave at the single interface, and then study some interesting physical phenomena that comes with them. So as I said before, we have this problem, okay, single interface, and we like to set up the mathematics to do this problem correctly. We assume that we have a plane wave coming in from the left, coming in this way with a beta vector. Beta vector is usually called a wave vector or the K vector. And then it will be reflected plane wave. The reflected plane wave has a beta vector that points outward like this. Okay, and then I will have a transmitted plane wave. That transmitted plane wave I denote with the beta vector pointing like that. Then you can work out the E and H field of all these plane waves. The incident plane wave on the left, the reflected plane wave on the right, and then the transmitted plane wave at the bottom. Can you see that? So our next task is to write this out rigorously.
using Maxwell's equation and mathematics. So this is not as simple as solving a transmission line problem anymore. But it's good that you go through this exercise so that you know how involved this exercise could be. Okay. So we study TE polarization. Okay. TE polarization is also known as perpendicular polarization. And it is also called an F wave in acoustics because it corresponds to, in acoustics, a shearing motion of a wave when the particles are moving in a shearing manner to affect the propagation of the same wave, which are called shear wave, or F wave. And this is analogous to an F wave in seismic or acoustics. Okay. So let's write down the solution in its full glory. Dipoles. And it's also called perpendicular poles. Okay? And sometimes it's called TE to Z pole. So let's assume that the incident wave is Y polarized and that it can be described by a plane wave. And then it can be described by a wave vector called beta I, then dot with the position vector R. We have studied this earlier in the course. We can write the plane wave solution succinctly using this notation. The beta I is that beta vector that you see in the previous slide. And from that picture that I have on the left from the previous slide, you can see that beta I would be a wave vector with an X component. Okay, and then a wave vector with a Z component as well. Okay, and you can see as surmised that the Z component of this beta vector should be negative. Okay, it should be negative. And that actually it's not negative because in my picture I choose to put the Z axis as pointing downward. So the Z component is not negative. So exactly that coordinate. But you can do the same thing to the reflected wave. Okay, you can do the same thing to the reflected wave. And E sub R would be also Y polarized, but with an amplitude that's not known, and let's call that amplitude E naught times R. And then multiply by a plane wave function that correspond to the plane wave propagating in the beta R direction dotted with R. Okay, and we can write down beta R. Beta R would just be X, beta X. And let's, without loss of generality, assume that we don't know what this X component is. Let's assume that it's beta Rx minus Z, beta RZ. Okay. And then we write down the transmitted wave. Transmitted wave will be similar, still polarized in the y-hat direction, as we have shown in the picture over there. Then E0T, let's call this RTE and TTE, since they are TE polarization, e to the minus j beta T dot R. Okay, and beta T is something that is X hat beta Tx plus Z hat beta Tz. Okay. So our next task is to find this coefficient. There are two unknowns in this problem, RTE and TTE. Okay. So I have two unknowns. I need to find two equations. And where would I get those two equations from in order for me to solve for these two unknowns? Anybody? Yes. The electric boundary conditions, very good, all right. What are those? Do you remember them? At the dielectric interface, what are the boundary conditions that we have?
Your thermal functions of the particular point H is going to be boundary.
Yeah, those are all correct. Okay, those are all correct. Curl of E is bounded. So from curl of E being bounded, it refers to condition E must be continuous. Okay. The other boundary condition you're probably referring to the one for the magnetic flux divergence of B equal to something. But lo and behold, something you should keep in mind is that for electrodynamics problems, solving the first two equations are sufficient. We don't have to involve the third and the fourth Maxwell's equation. So we should ask ourselves, is that if Faraday's law is right to tangential E be continuous, we should only look at Ampere's law now. Okay, we don't have to look further down with it because the third and fourth equations are redundant. So if we invoke Faraday's law now, what boundary conditions should we get at the interface? Curl of H is blah blah blah. Curl of H has to be finite. That implies something about H. Anybody? Curl of E is finite. Implies tangential E continuous. Curl of H is finite. That means there's no jump in the field, implies N cross H is continuous. Agree? So tangential E is continuous, tangential H is also continuous. Those two boundary conditions follow from the first two Maxwell's equations. Since there are two unknowns, we need to invoke and impose these two boundary conditions. Okay. So let's impose the first one, tangential E continuous. And the tangential component is very simple in this problem. Here are the Y components of the electric field. Then if I impose that, if I write things in full glory, I should impose the boundary condition at Z equal to 0. Okay, I impose the boundary condition there. I write down these three expressions, but setting Z equal to 0. So if I were to write down the total field in the upstairs, it will be EI plus ER, Z equal to 0. You should write this way. Should be equal to ET at Z equal to 0. N cross. I should take the N cross of all these quantities. Okay. Taking N cross of all these quantities will give me the tangential component. And they should be continuous at Z equal to 0. Okay, so even this is symbolic, I can already figure out what the tangential component of E is. They're just a Y component now. So if I were to impose this boundary condition, then what I should have is that this quantity E0, e to the minus j, beta I dot R, if you remember what beta I dot R is, it will be beta I x plus beta I z, right? Beta I has two components. If you take the dot product, you get that thing. And they're supposed to set z equal to 0, so beta dot r will only have one term. So the exponent simplifies. So if I were to rewrite this exponent out here, it will just have one term in the exponent. Okay, and then the second term will be RTE, or E0 RTE, okay, which follows from here. And then what I have, the exponent will be beta Rx x. My handwriting is a little bit sloppy, but you know what I mean. Okay, and you see the second term is just that. And then should be equal to the right-hand side, which is E0 T TE. Kind of getting sloppy now. I have to find a way to write this. Oops. That's very small. Okay, I have to find a way to write this down. So there should be e to the minus j beta txx. Can you see that? Okay. I can cancel the e naught everywhere. You cancel the e naught on the left hand side and the right hand side. So I have exponentiation of something to the power of x. And you cannot get these two equations equal to each other. For all x, unless I do something. Does anybody remember what you had to do as an undergraduate? In order to get this equation equal to each other, you do something. Let me erase it so that I can write this right-hand side more clearly. So if left-hand side equals to the right-hand side, and this equation is supposed to be equal to each other for all x. This is a mathematical way of writing for all x. Okay. What is the simple way to make these two equations be the same as each other for all x? So what is the simple way to get these two equations to be equal to each other for all x? Depends. For the betas, very good. Sorry, I heard you wrong. All the betas are equal to each other. Then exponentiation terms are equal to each other. You can cancel them out. Okay, very good. That's excellent answer. So we need to impose that beta x I Rx is equal to beta Tx. Okay, then this term will cancel with each other. The E naught will cancel with each other. Okay, this condition is the same as imposing all the bases of the three terms are the same as each other. This is called phase matching. Okay, this is called phase matching. And sometimes it's also called momentum matching. Remember that the momentum of a photon is h bar k. Okay, so it is also called momentum matching. And then if you look at this equation, after simplification, it just is 1 plus RTE to TTE. Okay, we have one equation, but two unknowns. So we need to do the other equation. So the other equation is obtained by matching tangential H continuous. And you go back to Maxwell's equations. Okay, you go back to Maxwell's equation, and then you find the HI
And if you were to impose Maxwell's equations, then you get something that looks like beta I cross EI over omega mu1. Okay, beta I is what you have because del becomes minus j beta under the plane wave approximation. If you use all this, then the plane wave becomes very simple. You can find the magnetic field quite easily. You can also find that for HR, beta R cross ER over omega mu1, and then you can find for HT okay, so then you mesh tangential component. You know how to do cross product. I wouldn't go through the detail with you know how to do that. Then the next tangential H component. And in detail, the devil is in the detail. Okay. And after you have mesh boundary conditions, again you assume phase matching. And then you end up with an equation that looks a little bit horrible. Beta IZ over mu 1 minus RTE is equal to beta TZ over mu 2 TTE. So we have two equations and two unknowns. We got this first equation from the previous slide. And then now by matching tangential H, we get the second equation. And you might be wondering where the beta Z's come from. Well, we're taking the cross product of the E field with beta. E field was pointing in the y direction. So the cross product picks up the Z component of beta. So you go to the algebra. So finally, you end up with an equation that looks like this. The details are written out in the lecture notes. I wouldn't go through the details. So with this equation and the previous equation from the previous slide, you can solve for the reflection coefficient. And you can also see that beta IZ squared plus beta IX squared must be beta 1. And what kind of relationship is this? Is I say in region 1, where the incident field is there, I must have beta IZ squared plus beta IX squared must equal to beta 1 squared. Sorry. What do we call this relationship? Very good. Dispersion relation of same. Okay, very good. So if you make use of this relationship, and furthermore, that the reflected wave is also in region 1. So this must be true for the reflected wave. And then these two are equal to each other by phase matching. And from this, you can conclude that beta IZ must be equal to beta RC. Okay. However, the Z components of the beta vector are not equal to each other. Okay, you'll find that beta TZ squared plus beta TX squared is equal to beta 2 squared. The dispersion relationship for region 2 must be satisfied by beta T. We have this relationship. But beta 2 is not the same as beta 1. If you compare this equation, the X components are all equal to each other due to phase matching. These are all equal to each other. So it's quite clear that beta TZ is not equal to beta IZ, which is equal to beta RC. So beta IZ, beta RZ are equal to each other, but not beta TC. Is this clear? So because of this, you can solve this equation quite easily, but you cannot assume that beta IZ is the same as beta TC. You cannot cancel it. And after solving them, then you end up with the reflection coefficient shown by this slide. Okay. You can get the TE reflection coefficient or the Fresnel reflection coefficient. And you have the fact that 1 plus R must be equal to T. You can find the transmission coefficient quite easily. And these are somewhat analogous to the gamma of the transmission line theory. You have found gamma, and what it should be for a simple reflection at one transmission line problem. This is just something very analogous to that. Except that when you do it here, you have the dot I property. You want to solve full Maxwell equation. But slightly more painful, but it worth it. Okay. Any questions regarding this? And it turns out that this reflection coefficients are known around 900 Islamic world as well. And then you can go through the other polarization, which is obtainable by duality principle. Okay, you can get the other polarization for the magnetic field by using duality. I wouldn't go through that. But let's look at what kind of interesting phenomenon that we can have. Okay. So let's look at total internal reflection first. Let's look at total internal reflection. And then if I look at R12TE, I write it down again. It is beta 1Z minus beta 2Z. Okay, I'm using 1 to denote region 1 and 2 to denote region 2. So the beta Z's in those two regions are beta 1Z and beta 2Z instead of beta. Okay. So this is the reflection coefficient that we have. And there is something interesting here, which is that there are occasions where you can make beta 2Z to be pure imaginary. If you take a situation where beta 2Z is pure imaginary, then you have what is called the total internal reflection. When does that happen? That happens is that you can think of phase matching as that if you have a K vector, okay, the reflected wave vector looks like that. And then if you have a transmitted wave, let's assume that the transmitted wave is bending that way. Okay, this is beta T. Beta I, which is the same length as beta R. So when you have phase matching, you're actually requiring the X component. Let's assume that this is you're requiring the X component of this beta vector to be equal to each other. But you can have occasions where this matching is not possible unless something crazy happens, which is that you have total internal reflection. Okay, say, let's assume that region 2 is optically less dense, or where the permittivity is lower than region 1. Okay, you have maybe mu1 epsilon 1, mu2 epsilon 2. Let's assume that mu2 epsilon 2 product is less than mu1 epsilon 1. Okay, in that case, you can quite easily show that the transmitted wave vector will be refracted away from the normal. And if you make the angle of incidence large enough, it will keep being refracted more, and finally it becomes horizontal. Oops. Okay, so if you keep increasing this angle of incidence, the refracted wave in the transmitted wave will become bigger. This theta t will become bigger. And finally, there will be an occasion where the wave comes in and then the reflected wave will just become horizontal. Okay, let me see if that is right. This is not a good picture. Okay, the reflected wave is like that, but beta t becomes horizontal. Okay, you have beta r pointing like that and beta I pointing like that. But beta t can become horizontal or parallel to the input. That is when you have total internal reflection. What it means is that if you were to make the incidence angle bigger than that, beta t will become beta tz, which is square root of beta 2 square minus beta x squared. So if you keep increasing the angle of incidence, beta x is beta 1 sine theta I, for instance. Okay, you can make beta or theta I bigger and bigger, beta x will become bigger. And they will come to an occasion where beta x is larger than beta 2. The beta 2 is a fast medium, or it's optically less dense than beta 1. Okay, they will come on the occasion where beta Tg becomes pure imaginary. And when that happens, the wave becomes evanescent. And you kind of indicate that in this picture over here, this is not the good picture. This is the picture where beta 2 is larger than beta 1. Okay, and this is just a diagram to show phase matching. With the beta vector coming in, beta r reflected, phase matching means that beta t has to be pointing in a certain direction so that the x components are equal to each other. The x components of all these three vectors are equal to each other. And that is the phase matching condition. So you can make beta in the second region large by increasing the permittivity and permeability. And phase matching always requires these three vectors to be aligned in this manner. Can you read this picture well? Yes.
Can you display the diagram full screen so you can put on the left half corner?
Okay, let me see if I explain full screen. Is that what you mean? It has to think a little bit before it can display. I don't know why it takes so long. Okay, finally it comes. Okay, can you see it? So you can see that when beta 2 is larger than beta 1, this is the picture for phase matching. These surfaces are called beta surfaces or sometimes T surfaces. Because kx squared plus tz squared must be equal to t squared. We are equations of circles in the beta space. Okay, let me see how I can get out of this. The only way I know how to get out of this is to press the escape button. Okay, I get out of it. I have to let the screen refresh itself. Okay, it refreshes itself now. So, however, you can have this picture over here where the beta in the second medium is smaller than the beta in the first medium. You will have to draw this picture for phase maximum. You can see that when the angle of incidence for beta is larger than a certain value, beta t will become horizontal on the other side, that phase maximum condition. And if you go beyond this, beta t cannot be drawn as a real vector anymore. And actually it becomes a complex vector. A complex vector with an imaginary part in the z direction. Okay, not draw it, but this is the maximum that you can go when you want to draw this picture. And when you go beyond that, you will have evanescence waves, okay, and you will have total internal reflection. Okay, I wouldn't go through the mathematical details of this. I presume that you have studied this before in your undergraduate course. You can look up the reflection coefficients. They're all the reflection coefficient is density of 1. All the energy is going to be reflected. Okay. And so if you want a picture for total internal reflection, this is one that I can get from the internet. Very quickly, when you show that the wave comes in, it gets shifted horizontally a little bit before it comes back. This is called a boost tension shift. Boost tension shift because the reflection coefficient is actually something of unity, but then the reflection coefficient would be something like A minus J B or A plus JB. Okay, when you have this reflection coefficient, one of the two terms, if you remember, this is something like beta 1z minus beta 2z over beta 1z plus beta 2z. When beta 2z becomes pure imaginary, okay, J alpha 2z, for instance, it becomes pure imaginary, then the Fresnel reflection coefficient can be written in this general form. And when you have something written in this general form, you can write it as a phase form where this is minus J2 phi. You can combine these two in polar coordinate system where phi is something like arctangent of B over A. Okay, you can use a polar mathematics. And this reflection coefficient becomes something that has a pure phase shift. So if you have a phase shift in the frequency domain, what does it mean in a time domain? You remember if you have a phase shift in the frequency domain, what? Yes. Yes. No. Let me say, these are all in the frequency domain, right? They're all in the frequency domain. And this reflection coefficient can be written as a function that has a pure phase change. If a phase change in the frequency domain, what does it correspond to in the time domain? You know what that is? So if you have a phasor is been changed by a okay, if you have phasor, you do a phase shift with the phasor, and then if you convert it back to the time domain, it will be multiplied by e to the j omega t and taking the real part of this thing, right? You go through the usual ceremony of this, then it will be cosine of omega t plus phi, right? If you go and convert this function back in the time domain,
any phase shift in the frequency domain corresponds to something in the time domain. What do we call that? Phase shift in frequency domain is the same as if you're a signal processor, you should know that phase shift in a Fourier transform signal is corresponding to a time shift. Okay, time shift in the time domain. So when we have this phase shift, it corresponds to the time shift. So if you were to look at this thing in the time domain, you'll find that there's a delay in the reflected light coming back at you because of this phase shift. And that shift is called a loose tension shift. Okay. You can have total internal reflections, and those were wonderful things to have. So this you can make the waveguide for a beamform waveguide, for instance, and the wave can bounce back and forth within the two interfaces. And this beamform waveguide can act like a waveguide, where the wave is completely trapped between the two layers. Okay. And of course, this is the principle behind how an optical fiber works. An optical fiber is, of course, a lot harder to analyze. It has a cylindrical interface. You have to use Bessel function to analyze that interface. But the physics is the same. The phase matching, and then you have total internal reflection and those interfaces. Because of the phase matching condition. And then in the optical fiber, it bounces back and forth. This interface is causing the light to be very tightly confined. And this gives rise to the physics behind an optical fiber. And this optical fiber has transformed our world. You know why it transformed our world? You don't know. Fiber optic communication. Why is fiber optic communication so important? Yes, the loss is very low. That's a correct thing to say that. Yes. Fast is also correct to say that. But what is another way of saying that it is fast?
High bandwidth.
Very good. High bandwidth. You're an optics guy, so you know. Okay. It's from Creel in Florida, right?
Orlando, yeah, Florida.
Okay. So when you have high bandwidth, when you can work with optical signals, the bandwidth is humongous. Because before that, we only have radio signals. So your AM 920, your FM 101.3. And when you go to microwave, you can even have communications with a larger bandwidth. And then you go to your cell phone, which has bigger 8 hertz bandwidth. Okay. Then you go to optics, you can have very huge bandwidth. And bandwidth allows you to carry very high data rate or fast signal. Okay, so optical fiber has transformed our world in a sense. So the next thing I'd like to talk about is actually the Brewster angle. Okay, and if you look at the Brewster angle, and if you look at the Fresnel reflection coefficient for TM wave, it is somewhat different from that of the TE wave. Okay, this is the RTM, Fresnel reflection coefficient for the TM wave. How would RTE look like if you were to invoke the relative principle in your head? Yes? Yes, very good. Solve the epsilon with mu. Okay, but in this world, it's very strange. Most magnetic materials have nu of 1 at optical frequency. But most materials do not have dielectric constant of 1. So if you elevate this Fresnel reflection coefficient to optics, okay, there's not very interesting things going on for RTE because nu is equal to 1. Okay, but there is something quite interesting for RTM because epsilon is not equal to 1. So RTM is the polarization that sense and feel the difference between epsilon and nu. Okay, we actually sense the difference in the permittivity. Because of this, there are occasions where you can set this numerator to be 0. You can get these two terms to be equal to 0. Cancel each other. For RT and for RTE, it's not possible if you want to make beta 1z equal to beta 2z. The only way you can make them equal to each other is to make the two materials to be the same. But for RTM, you don't have to make the two materials to be the same. You can get this cancellation going on. Okay? And from that cancellation, you arrive at something called the Brustol angle, where the reflection coefficient goes to 0. Do you want me to derive this formula for you, or you have had it in your undergraduate course before? I presume that you have it in your undergraduate course. Yes. Derive it? Okay. Let me see. So you set this to be 0. Okay, this is not possible. This equation is not possible, but however, if you have this equation, epsilon 2 beta 1z equals to epsilon 1 beta 2z, then the numerator of this reflection coefficient will go to 0. It turns out that this equation has a solution. How do you see that? Well, you see that because if I were to square this equation, okay, if I were to square this equation, I'll go a little bit fast. Okay, I square that equation and get that equation. Okay. And then you can solve this equation. It's just algebra. You only have one unknown in this equation, which is beta x. Okay. You can solve beta x to be omega mu epsilon 1 epsilon 2 over epsilon 1 plus epsilon 2. I make life simpler by making mu 1 equals mu 2. Okay, and that happens in optics most of the time anyhow. And then when beta x equals that value, the reflection coefficient is equal to 0. And that is possible. That is possible. And I worked out some math in the lecture notes. Okay, I don't think I will go through that math in the lecture notes since we are missing one lecture because of the fall break. Next Tuesday we don't have lecture. I want to go a bit faster so that we can cover the lecture that we missed during fall break. Okay, so you can actually work things out. You can show that if we have Brustol angle, that happens at an angle theta 1, theta 2, that this equation will be satisfied. Okay, and you can show that theta 1 plus theta 2 is pi over 2. Okay, it's shown in the lecture notes. I won't derive it for you. And then what happens is that in this particular angle of incidence, which is the Brustol angle, then the waves get refracted, but nothing comes back in that direction. And this is like to explain it this way. This is TM polarization. So the magnetic field is parallel to the surface. Electric field is not parallel. So as the wave refracts into the medium, all the electric fields are pointing in that direction. And they give rise to electric dipoles, or they induce electric dipoles. But electric dipoles are all pointing in that direction, they cannot radiate in that direction. I don't know if you understand the notion that if I have an electric dipole, the electric field looks like this. Magnetic field looks like this. Can you visualize it? Electric field and magnetic field from electric dipole. And if you now take E cross H in your mind, E cross H is 0. And you just do E cross H in your mind. So that's field distribution. Can you see that E cross H is 0 in the axis? Electric dipoles don't radiate along the axis. Because of that, those electric dipoles in that direction, and hence we have booster angle effect. Okay, so if you were to plot the reflection coefficient, you'll find that the Tn reflection coefficient is always smaller than the Te reflection coefficient, because the Te reflection coefficient does not have the booster angle. But the Tn reflection coefficient is due to the fact that the magnetic field is horizontal, electric field is vertical. This is Tm. Okay. But when you have Te, then the electric field is horizontal, the magnetic field is vertical. Okay. So light are randomly polarized. We don't divide themselves into these two polarizations, as you can see here, but they actually distribute themselves randomly between these two polarizations. So you can see that now imagine in your head that you have a randomly polarized light coming in at the interface. The one that where the electric field is horizontally polarized is always reflected more than the electric field that is vertically polarized. Vertical means in this direction. So one of the two polarizations is always reflected more. And hence after reflection, the light is not randomly polarized anymore. The light has a preferred direction of polarization. And this is used in photography. Okay, that you put the correct kind of filter in your photographic lens, you can make a drastic difference between these two. The last picture has a lot of reflection from the window mirror, because you have both Te and Tm polarizations there. However, you can have a filter that takes out one of those two polarizations, and the image is drastically changed. You don't see the glare from the window surface anymore. Another case where you can make use of this booster angle effect is in your sunglasses. The sunglasses, you will bifurcate once, and they will reduce broad glare. Broad glare has the preferred polarization. For the same reason, the RTE is always larger than RTM. Okay. And you can read about this in the lecture notes, because I just want to go a bit faster so that we cover a little bit more materials today. Okay, are there any questions before I end? Okay, I'll stop here and let you go.